So good afternoon, everybody. Thanks for coming to the session on dynamic regimes of space plasmas, deterministic or stochastic. We have two talks at the oral session and several posters at the corresponding session. So we're starting with Marcus Ashwanden, who will talk about statistical and physical aspects of self-organized criticality, solar flares, and astrophysical phenomena.
Thank you. So I would like to talk a little bit about the universality of self-organized criticality, and we got some exciting new results, especially in solar flare statistics, that give you some new insights. So I will first give a little bit, for this broad interdisciplinary audience, a little bit flavor in other areas where self-organized criticality is interesting. You see here there is a list, the mostly astrophysical phenomena from galaxy formation down to solar stellar flares, Saturn rings, and so on. They all show Pauli distributions and have been associated with self-organized criticality phenomena. And actually, even the publication of in a certain area, like here some books about self-organized criticality, is an avalanche. As you can see, 3 outcoming in a year. So these are the most recent ones. Originally, it all started with Per Bach with the classical paradigm of a sand pile, although they had some difficulty to reproduce the power laws in the laboratory. Actually, it looks like natural systems do it much better, like solar flares or pulsar glitches. And then the first attempt to understand them theoretically was to run stellar automaton simulations, and they could reproduce the power laws in sizes and in sizes and time scales. And here I show you one of those stellar automata models. So you see that there is just one single pixel was disturbed that was above the critical threshold, and that triggered next neighbor interactions, pushed them out of equilibrium, and so on. So this is a very long avalanche, of course, in a much longer series of millions of time steps. But what you see is just to mimic complexity, you can just with a simple mathematical redistribution rule, and there is such a threshold, and the redistribution, that's all there is in there, and it reproduces all this complexity. You cannot easily quantify that with macroscopic parameters. But power laws have been found in many systems that have some multiplicative chain reactions, so even human activities like city growth, word frequency languages, stock market fluctuations, traffic jams, network, internet access, you get these power laws. In biophysics, evolution evolved in punctuated equilibria, so you have some times where you have intermittently a large number of species get generated by mutation or die out. How the brain works, neural connections, connectomes, how they also have been associated. Then, of course, you know examples in geophysics like landslides, earthquakes, forest fires. Magnetospheric physics, which is maybe more at the heart of this community here, auroral phenomena, magnetotail current disruptions, substorms, bursty bulk flows, magnetic field fluctuation in the solar wind, auroral UV images, and auroral electron jets. They also have been found to have power laws, but there is a little bit of controversy whether they were externally driven or internally self-organizing. But I will bring up statistics of solar flares, and solar flares, they probably, like CMEs, they produce fluctuations in the solar wind, in density and magnetic field, and so they have also implications as shock drivers for collisional processes in the geospace, such as foreshock and magnetotail plasma sheets, as you know. And there are some simulations, like from Sandra Chapman, where they could reproduce not only the power law, but also there is a pileup because of a finite system size, that you get more event at the upper end of the distribution. And that has been observed for auroral emission. And then Takalo, he went a step farther. He didn't use just a self-organized criticality system that had a constant input. He pushed the input out by a larger disturbance, basically to mimic the influence of a solar flare on the bow shock of the Earth or on the geotail. And the system automatically evolved back into the critical state, so it was kind of robust, and he could mimic both externally triggered substorms as well as internal substorms in power law-like distributions. Now you see also power laws in, say, the distribution of crater sizes on the Moon, solar flares. This is an extremely nice power law over 4 orders of magnitude in the peak flux of hard X-rays. And this was actually published by Brian Dennis in '85, even before the idea of self-organized criticality originated in '87 by Pierre Bach. And today we have now data that span over 8 orders of magnitude from 10 to 32 ergs for the largest giant flares, like the one on the shown on the right side. That's about 200,000 kilometers long, and this about here in the distribution, all the way down to nanoflares, which are just small coronal loops that stick out of the transition region, but they flare up like a flare. And because of the 8 orders of magnitude is mostly a result of the volume. So in spatial scale is maybe 2 orders of magnitude, but the volume is then 6 orders of magnitude, so that's why you get this huge inertial range for power law behavior. So far, we haven't managed yet to derive them all from the same data. These are from different data sets, different instruments. But right now, with Solar Dynamics Observatory, actually, we can get those data. So these are early simulations. But basically, this is the connection of a cellular automaton model with a flare evolution. In a flare evolution, it's almost like a sequence of dominoes that are lined up at a neutral line, and wherever the magnetic field is stressed, it propagates like a domino chain reaction. Stellar flares, there we have less statistics. Usually only the top part is sampled, so they see some trunk-off effects and get usually much steeper power law slope than we get for solar flares. And I don't want to go into galactic, that's a little bit speculative. But what is universal about power law distributions? Because we observe them in earthquakes as well as in solar flares, there must be something universal that does not depend on the physics. And can we predict the values of the power law slopes and which parts are actually due to some physical mechanism? I published a model that has 4 elements. One is the scale field probability theorem. If you roll dices, you get a binomial distribution. This is with 3 dices, all possible combinations, and you see already a Gaussian-like distribution. So if you just do a random on a linear scale, you get the Gaussian distribution, which at the tail is exponential or Poisson. So that's certainly not a power law. How do you get a power law? This is the size of where you can have nonlinear energy dissipation, say the global surface for earthquakes. How many earthquakes you can have that span over the whole globe? Only one. If you go to earthquakes that are a factor 2 smaller in size, obviously you can break that into 4 pieces, so you get 4 for a factor 2 down. And so forth. For 4 times smaller, you get 60 times more. So you see you end up with this power law distribution size -2. And you can generalize that for any dimensional space, for 1-dimensional, 2, or 3-dimensional. And so that alone predicts you the size distribution should go with the length scale to the power minus the dimension of the system. So for the real world, 3-dimensional world, it would be L-3. And it's a very important key. So you already have a prediction for one distribution. First of all, you get a power law at all and not a Gaussian. And it gives you the slope, -3. So let's see if that works. So far for solar flares, we did size distributions, and we get indeed something like 2.9, somewhere in the neighborhood 2 to 4. So kind of 3-ish. So it seems the data support this hypothesis that the length scale distribution is -3. Once you have 1, then you just need to know the scaling laws to other parameters and can derive any other. So now we did some new work with SDO. Actually, this is still from Trace from SDO, the Solar Dynamics Observatories, for the biggest 150 flares. And when we put them together with the nanoflare, so that gives you spatial scales over about 2 orders of magnitude. And the average, independent of the wavelengths we observe, is something like 3, and the theory predicts -3. So it's universal, at least in the sense it doesn't depend on the wavelengths, and the wavelengths that, that depends on the temperature, densities of the plasma, and so on. So it seems to be scale invariant. The second ingredient of this model is that the spatio-temporal relationship is you can describe by diffusion, by fractal diffusion actually. And so this is again this avalanche. I showed the movie first. When you do the envelope and measure the radius, it goes roughly with time to half. So that looks like it behaves like classical random walk, how the avalanche evolves inside this volume. And so it's basically consistent with random walk. Here, this is how the size of the avalanche evolves, and this curve is t to a half. This is how the fractal dimension evolves during the same avalanche that I showed you in the movie. So it's more or less always 1.5, which you expect if the lower limit is about 1, and this is a 2D simulation, is 2, so you expect the average fractal dimension to be about in between, so 1.5. So you have 2 ingredients already, the length scale distribution L-3, and then the fractal diffusive or random walk. And so you expect for the timescale distribution, so then you can calculate directly what you get for the timescale distribution, because you just substitute this dependence, you know the distribution of length scales, and then substitute this scaling law between L and T a half, and then you end up with T to -2. And this is statistics from 3 different satellites with solar flares. The timescale duration is in the average about 2. So that seems also to be universally valid and doesn't depend on the physical mechanism. Now you can generalize this diffusion a little bit more from classical diffusion to subdiffusion, superdiffusion, so you have a different diffusion coefficient, and I analyzed that too, and this is one solar flare evolves, it gets complexer and complexer. This is the radius of it increases, this is a fit of this diffusion equation, and you end up with a diffusion coefficient statistically about 0.5. So it seems to be subdiffusive for solar flares, probably because of the anisotropy of this magnetic field. Now I have only a few minutes more. Fractal dimension you can measure in solar flares or in such simulated avalanches, and we could prove it goes fractal, like here. This is for the Bastide flare. So you have a third ingredient. The area is fractal, the internal structure of the avalanche. From that you can calculate, the distribution of areas, the volumes, just by substitution of these parameters. You get these spreading exponents and coefficients. And when you measure, this is now the areas of solar flares over something like 4 orders of magnitude. It's about predicted 2, and it's indeed 1.98 for every wavelength. So again, this is still invariant, seems to be universally valid. It doesn't depend on the emission mechanism, temperature, or any physical parameters. And then the last, if you observe a flux in a wavelength, then there is some scaling between the volume that emits, and so that's an unknown. But to first order, you can assume 1, because for optical scene emission, EUV, soft X-rays, that works pretty good. So that's basically all components, and with that, you can predict what distribution you get for fluxes, for fluences, for total energies with those power law slopes. But the last part, so this is all with different colors, with different wavelengths, you get the same slope, so it really seems to be a universal scaling. And I think I don't have much more time, but I want to just, as a final note, say, not all power laws are self-organized criticality. There are other turbulence, percolation, chaotic systems. They have power laws in common for some parameters, but they don't fulfill some of the criteria. So not everything of power law is a self-organized criticality system, But I think we have now an understanding why there are power law slopes and what the power law slopes are for different parameters, and which one are universal valid and which depend on the physical emission mechanism. Thank you.
Thank you so much for a very broad and inclusive review. We have time for one or maybe two questions. Yes, good job.
The spatial scale, so I derived it from the area, basically just the equivalent circular area, and the radius gives this scale. Now, for three-dimensional flares, I assumed a semi-spherical geometry. So that's roughly 1 or 2 density scale heights.
Any other questions? Okay, I think we should better move on. So the next talk is by Sasha Ukorsky, and it's titled The Complexity of Radial Transport of Radiation Belt Electrons at Earth. It is also an invited talk.
Thanks, Dimitris, and I would really like to thank the conveners for inviting me, and I really appreciate the overarching goal of the session. It's dynamic regimes of space plasmas, deterministic and stochastic. So if there is really any point of the talk that I'm trying to give now is that the one of the first discovered system in space plasma's radiation belt really behaves in a very complex stochastic fashion. The outline of the talk is very simple. I would like to say just a few words about historic review, about the background of discovery of the belt. But now we're really excited because we have a new mission. Closer to the microphone? Okay. So we're really excited because we have a new mission, Van Allen storm probes, and we're going to the first discovered system with new instruments and new data, and I'm going to try to motivate why is it important to do so. And the reason is that because the system is really complex, in fact. So just a historic slide is that radiation belts and the transport in radiation belts was discovered in very, very first pioneering mission going simultaneously from United States and Soviet Union, the outer belt and the inner belt. It was a shocking, fantastic discovery that, in fact, the near-Earth space is populated by high-energy particles. It is very important also to put this discovery in the context because this kind of explains how then it took the theory and understanding of radiation belt was developed. And what I would like to point out that, a little bit earlier, prior to the discovery and simultaneously to the discovery, there were some fantastic laboratory experiments of particle acceleration and cyclotron devices. It was realized that particles in plasma could be accelerated by high energies due to interaction with random phase electrostatic waves. And soon after that, there was basically one of the biggest discovery in 1960s plasma theory, the development of quasi-linear theory that predicted that wave-particle interaction can be described in terms of the Fokker-Planck equation in the velocity space. But coming back to radiation belts, the first theoretical papers really looked into the stability of particles trapped in the radiation belt. And it was realized that particles, in fact, can be trapped in stable orbits that are characterized by the superposition of 3 periodic motion that would be gyration, around field lines, the bounce motion, and the drift motion around Earth. And each of these motions are characterized by its own adiabatic invariance, and timescales of these motions are really well separated by multiple orders of magnitude that basically determine stability of particles trapped in radiation belts. But soon it was realized, also in 1960s, subsequent missions went up and realized that radiation levels across the belt vary quite a bit with time. And at that time, it was thought that basically the background field that particles are embedded into is very static. So it was, with the analogy of quasi-linear theory in the laboratory plasma, it was suggested that particles are energized in the process of random wave-particle interaction that lead to particle transport across the radiation belt and subsequent acceleration because of the conservation of the magnetic moment. Also, you need to somehow inject particles from the tail to the inner magnetosphere, and early theories predicted that basically it's slow changes in the configuration of the geomagnetic field allow particles to be transferred from the open to closed orbits and being stably trapped at Earth. Now we'd like to switch gears and basically fast forward about 5 decades, and we're here now, waiting for already analyzing Van Allen probe data, and now we're understanding first and foremost that radiation belts are really, a very dynamic environment. Radiation belts are embedded into really largely dynamic field which varies on the time scales from minutes to days. So actually the zero order particle motion is not the motion in a dipole field, but rather is controlled by large perturbation in the global geomagnetic configuration. Also, we understand both, with the development of first principle, like global MHD models, as you see on the left panel, and some recent spacecraft measurements, that the convection of plasma from the tail to the inner magnetosphere is not a very simple, laminar process that puts plasma from the open to closed drift paths, but it's rather is a superposition of very small scale transient activation that produce the buildup of hot plasma in the inner magnetosphere. And as a result of the buildup of this, hot plasma, you have large scale electrodynamical system that really perturbs leads to large-scale currents that flow both, around Earth and into the inner magnetosphere, but as a result, really dramatically change the distribution of magnetic field across the inner magnetosphere. And also using test particle simulations and other theoretical models, we understand that these, large-scale perturbations of geomagnetic field can really affect distribution of trapped radiation across the inner magnetosphere. So as a result, you have initially trapped population, and then you have a geomagnetic storm, and during the main phase of the storm, you have a buildup of ring current, and this is the distribution of magnetic field as you see in this series of plots on this figure. So the magnetic field in the inner magnetosphere really drops down because of the diamagnetic effect associated with the ring current, and as a result, radiation belt particles, trapped radiation belt particles, are transferred from from closed orbits around Earth to open orbits, and really gets pushed out from the magnetopause, which creates, dramatic magnetopause losses during storm main phase. And this was recently confirmed by a number of papers, and this is just like one paper, one result that shows that in fact during a geomagnetic storm you see these dramatic dropouts over a broad range of L shells that are not really associated with any precipitation into the atmosphere. So the idea is that particles are being pushed out through the magnetopause. All right, now we understand that particles are really subjected to global configurational changes of geomagnetic field, but still you need to somehow put particles, transfer particles across drift shells to create radial transport and to create subsequent particle energization. And this actually, the difference between understanding that we had in 60s and now is that you don't necessarily need to have random phased wave fields. You can just ensure that the wave harmonics in your driving wave field have large enough amplitudes so that particle populations trapped in neighboring harmonics of the spectrum overlap, which would allow transport in energy and L shells. And on the right here, you see kind of a realistic animation that shows realistic transport in three-dimensional dynamic field. So on the top panel, we kind of see the equatorial cross-section of particles with their energies marked by color. On this panel, we show the second invariant, which is also being violated during the transport. And here there is distribution of particle energies. And initially, we started just like with one energy drift shell value, and due to the interaction with regular but large enough amplitude disturbance coming from the solar wind, we induced the transport that produced particle distribution and energization in energies. Well, that's an interesting symbol. I don't know what that means. But the point of this slide is actually to compare what we understand now with initial kind of analogy with quasi-linear theory that people use in 60s. By looking at detailed test particle models of particle transport due to interaction with ULF fields, we now understand that transport is actually not in a good agreement with diffusion approximation, which is basically the quasi-linear theory. And realistic transport does not follow the distribution of kind of the spread of particle population, does not follow the scaling predicted by quasi-linear diffusion, but rather has a very complex nature. So a very similar driving condition could end up, producing very different response in global state of the radiation belt. You can either have increase or decrease of radiation levels across the belt with, having very similar solar wind conditions. Also, the difference is that we now understand that there are some very dramatic driving events which are associated with the arrival of interplanetary shocks that, as shown in this animation, courtesy of Brian Kress, that produce really large amplitude magnetosonic waves propagating across the belts, and particles that can kind of have right enough conditions, drift bounce conditions, can serve the front of the wave and be transported on very, very fast time scales from the outer belt to the inner belt and get rapidly energized, which is, another complex factor in understanding global response of the belt. Finally, it's interesting that one of the well-known old phenomena called drift orbit bifurcation really kind of shed new light now to understanding global response of the belt. So the classic kind of donut shape trajectory, the drift bounce trajectory of radiation belt particles is not the only mode the quasi-trapped or trapped radiation can be at. Another kind of behavior could be associated with a compression of the magnetic field due to solar wind dynamic pressure, which produces so-called drift orbit bifurcations, which is illustrated in this figure by this blue trajectory. So as instead of like being on a stable donut-like shell, you can see particle being initiated at the night side. It kind of goes to the day side, and then is transported off the equator to higher latitudes, traverses the day-side magnetosphere, and comes back. But as a result, as you can see, the particle is not on a closed orbit. So drift orbit bifurcation really is associated also with transport. And as I've said, it's a well-known phenomenon. I mean, first, I think one of the first mentioning of this phenomenon is the famous Northrop and Teller paper from 1960s. But now we realize that drift orbit bifurcations are associated with the separatrix crossing in phase space, and at separatrix the time scales of bounce and drift motion become comparable, and as a result the particle motion is no longer adiabatic, and bifurcations are associated with breaking of the second invariant and resultant radial transport because of that. We also understand that bifurcations now, because of the development of global models, really affect a broad range of radiation belt L shells. And we also understand now through more detailed modeling that bifurcations can be both associated with losses and enhanced energization of particles. And I'm afraid that I'm out of time, so I'm just going to put up these conclusions. But if there's one conclusion, is that despite the fact that we're dealing with the first discovery in space history, it's a very complex system, and there are lots of challenges that hopefully will be addressed with our new mission. Thank you.
Thank you very much. We have time for a very quick question, if there is one. No? I think we should move on to the next session. Thank you very much again.